Hey, welcome back. We are in Functions Lesson 11, and today we're going to be looking at something brand new here for us. We're going to be introduced to tables, maps, and graphs. A couple of these you are already familiar with. One will certainly be brand new. So let's read the following relation. Relation's a new word for you. We're going to be relating an idea and concept with some numbers, and we're going to write them as ordered pairs. So inside the rectangle here, if you're going to read along with me, please. In the scoring systems of some track meets, for first place, you get 5 points. For second place, you get 3 points. For third place, you can earn 2 points. And fourth place, you earn 1 point. So this scoring system is a relation. So it can be shown as an example, like this here, where in first place, you're going to earn 5 points. If you're in second place, you earn 3 points. And then what happens is the teams compete, and then the point totals are combined over like a Friday and a Saturday. That's how it used to be anyway. And then, of course, the team with the most points wins the track meet and so on. So that's a relation. You can also show a relation in other ways with using tables, graphing, and mapping diagrams. Now, the tables here, you're probably familiar with already. Here is an example for you. If you could add this to your notes, you've got the relation 2, 3, 4, 7, 6, 8. The first thing I'd like to do is draw your attention to the brackets. You see a bracket here and a bracket here. Well, this is called set notation. Set notation. Sorry about my handwriting here. Set notation. And set notation is just a way that we organize answers and actually select elements from something called a domain, which we'll talk about pretty soon. So high school teacher will expect you to know set notation. Nonetheless, back to our table here. If you ask the computer to generate a table, it's going to make a nice pretty table like this. Everything's symmetrical. You got colored boxes. But just in a notebook setting, in a practicality setting, you might just want to use something you might be familiar with already, a T-chart. So something like this. You could just say, you know what, I'm just going to do this and put a Y here. I don't know what the line's for. And make a vertical line, and put a line, and you're going to take the first ordered pair, 2, 3, x is 2, y is 3, second ordered pair, 4, 7, and so on. Okay? So we'll have the computer do its fancy work, write the relation by duplicating the ordered pairs as you see them. So we're just going to put 2, 3, 4, 7, 6, 8. That's a table. You could call it a T-chart as well. Either way works. Okay? How about this? How about we express the relation as a graph? Well, use the x and y values to plot the ordered pairs. Notice that all of these ordered pairs here are positive numbers. So we can focus in on quadrant number 1. So this is quadrant 1. If you recall, a coordinate plane, if I can get my lines anywhere near straight, you've got x and y. This is quadrant 1. This is quadrant 2. Do you remember this? This is quadrant 3. Maybe Roman numerals look like this with the lines over them. And what's the last one then? Well, this is quadrant 4. And there's a reason it goes backwards, counterclockwise like this. Again, something we'll talk about later. It has to do, again, a little foreshadowing, a little high school-y stuff here, called the unit circle. And that starts talking about trigonometry and calculus and stuff like that. But we're just kind of laying the groundwork for all this upcoming. So all these are in the first, so this is just focused on quadrant 1. Quadrant 1. You'll notice the first ordered pair, this is going to be then 0, 0 here. So here's 2, 3, here's 4, 7, and here's 6, 8. All right. All those squigglies, make them go away. All right. Now, something I'd like you to add to your notes, please. Write down what's in red. A function is a special type of relation that pairs each x value with exactly one y value. So this is the classic definition of a function. And that's really what we need to focus on, is every x value gets exactly one y value paired with it. So if we go back to our relation 2, 3, 4, 7, 6, 8, here's how we do a mapping diagram. Now, if you're not going to write anything else down, write down this, the mapping diagram. So just simply sketch what you see. You've got a little rectangular box with an X over it, a little rectangular box with a Y over it. They can be ovals. I've seen them as ovals. I've seen them just as straight lines with things underneath, but this is kind of a traditional mapping diagram here. Now, here's your rules here. Write all x values under x and y values under y, of course. But here's the important piece, from least to greatest. From least to greatest, okay? So we're going to put all the x's here. Remember that the x's are your first ordered pair, so it's 2, 4, and 6. And then, of course, all your y values are going to go here. And the y values being 3, 7, and 8. Now, you might say, well, what's the big deal? This looks just like a table. And you're correct. In this case, you're correct. Now, here is the part of the mapping diagram. Draw an arrow from each x value to its paired y value. This is called mapping. So if you look back at the relation, what number does 2 map to? 2 maps to 3. So we draw an arrow from 2 to 3. 4 maps to 7. So we draw an arrow 4 to 7. And 6 maps to 8. So we draw an arrow here. Notice that they're one-way arrows. They're not two-sided. They're one-way arrows. We'll talk about two-sided arrows later. Those are called one-to-one functions, but let's just focus on this. 2 maps to 3, 4 maps to 7, 6 maps to 8. So recall, a function always maps one x to one y. So this 2 maps to a single answer 3. This 4 maps to a single answer 7, and so on. This is a mapping diagram. Okay, let's say I ask you to express this relation as a table. As a table. Again, you've got a new relation here, 1, 4, 2, 5, 3, 3. So, fancy computer table looks like this. You can write your table how you want. How did we do a table? So, wasn't a table just a recreation of the ordered pairs? So if you did a T-chart or a table like formal like this, you would duplicate the ordered pairs as you were given them. 1, 4, then 2, 5, and then 3, 3, correct? Okay, so that's a table. We're going to assume you know the graph. Anybody can plot points on a graph. Well, you've practiced that since probably 6th grade. So let's just focus on the mapping diagram now. So what was the rules for the mapping diagram? Well, first, put your x and y and sketch your little boxes for a second. Okay, and now the rule said to take all your x's and put them least to greatest. So your x's in this case are what numbers? They're 1, 2, and 3. Well, that's pretty straightforward. 1, 2, and 3 will give us 1, 2, 3 there for x. And then what are your y values? 4, 5, 3. And again, we're going from least to greatest. So least to greatest means we're going to go 3, 4, 5, right? 3, 4, 5. Now, in this case, look back. Remember the last thing to do here is to draw an arrow from each x value to its paired y value. So looking at 1, what does the number 1 map to? 1 is attached to 4. It maps to 4. So we're going to go 1 maps to 4. Then 2 maps to what number? Well, 2 maps to 5. And finally 3 maps to what number? 3 maps, in this case, to 3. Is this a function? Yes or no? Why would it be? Why would it not be? So recall, a function maps one singular x to one singular y. So in this case, does 1 map to a single number? Yes. Does 2 map to a single number? Yes. Does 3 map to a single number? Yes. So the answer is yes, this is a function. All right, let's try this one on your own now. You've got a relation that has the order pairs 2, 3, 3, 5, 1, 3, 2, 4 as a mapping diagram. So draw your boxes, your x and your y, and I'll give you a few seconds here to get your work finished. Kind of linger around. While you're doing this, I'll tell you, just for whatever strange reasons, when you record these things, things happen, right? The tech fails, I make a mistake, etc. This is my 8th attempt at this video. 8th. I mean, my maximum retry was like 3. So I'm not sure what it is about this one. I do like the lesson, though. Okay, that's none of your concern. Shouldn't be. You have enough things going on in your life. That's my issue. Let's go back to this mapping diagram. You're going to place your x's in order from least to greatest. So what are your x's? Well, let's see. 2, 3, 1, 2. So you probably wrote 1, 2, 3. Now, I intentionally, sorry, if you did double up on the 2's, I intentionally let you do that. So what I want you to do now is erase one of the 2's. You never duplicate the values in a mapping diagram. Because we're going in a little foreshadowing, we're going to be talking about something called a domain. Domain and range. And when you talk about a domain and a range, that's really your X's and Y's. You never duplicate entries. So if you have 1, 2, 2, 3, just make it 1, 2, 3. Well, what does that say about our Y's then? 3, 5, 3, 4. Do you see the double 3's? So then we should just have 3, 4, 5. Okay. So I didn't tell you that, but I want you to just do it so that by backing up, you kind of remember. It seems to work out decently well. Now, back to our mapping. Who does 2 map to? Well, 2 maps to what number? It maps to 3. Good. Then who does 3 map to? Let's look at our second ordered pair here. All I'm doing is I'm looking at this ordered pair, and I'm looking at this one. 3 maps to what number? 3 maps to 5. Okay, that's done. Who does 1 map to? Right here. 1 maps to what number? 1 maps to 3. Okay. And then finally, let's look at 2, 4. And 2 maps to what number? 2 maps to 4. So I've got this here. And we're done. We've satisfied all of our ordered pairs and we've checked them. Now, is this a function? Why or why not? I see some straight lines. Everything has a place. All right, so in this case, the answer here is no. This is not a function. Why is this not a function? Well, remember our rule. 1x maps to 1y. So 1 maps to 3, and 3 maps to 5. But look at 2. 2 is the problem child here. 2 maps to 2, maps to 3, and 4. Maps to 2 different y values. So here's a way that it might help you remember. If you think of x's as, let's do this, people, and you think of the y values as places. So let's say a lunch table at school. Can person 1 be at lunch table 3? Well, sure. Can person 3 be at lunch table 5? Of course. Can person 2 be at lunch table 3 and lunch table 4 simultaneously? Well, that's a no. Person 2, this person here, cannot be at table 3 and table 4 at the same time. You could also think of classrooms. Like sometimes I get a new student and they'll have they'll have period 2, but they'll have period 2 twice. It'll say math and PE for period 2. Well, the student has to be in one place or another. Can't be in both math and PE period 2. So this is not a function based on this problem right here. Okay, let's express this relation 1, 1, and 1, 2 as a table. So maybe you just watch this one. You've done a little bit of writing here. So just the ordered pairs, right? 1, 1, and 1, 2. Okay, fair enough. If we graph this, we could graph it as 1, 1, and 1, 2. Okay? And then finally, a mapping diagram. 1 is our domain, our x values, and y is our y values, right? Because we don't repeat. So see how there's a 1 here and a 1 here? Well, we don't duplicate that. So it's just 1. So if we go back and look at this now, there are 2 reasons you can tell immediately this is not a function. First of all, if you connect these dots right here, don't these dots form what kind of a line? This is undefined. Remember that? From previous lesson, the slope here is undefined. And doesn't 1 map to this one and this one? So person 1 is in classroom 1 and classroom 2 at the same time. Impossible. Person 1 is sitting at lunch table 1 and lunch table 2 at the same time. Can't happen. Okay? So this is not a function. Does the following mapping diagram demonstrate a function? So let's take a look at this one. So take a look. You've got your x's on the left, your y's on the right. Function, yes or no? Well, what's the definition of a function? Every x goes to 1y. So let me ask this. Can person -4, and it's a funny name, be at lunch table 2? Sure. Can person -8 join them at lunch table 2? Also yes. So that works out fine. You can have more than one person at a lunch table or in a classroom. Can person 4 be in room 1? Can person 5 join them in room 1? Yes. So if you can remember, people and places, you can only be at one place at one time. So this is a function. Okay. That will do it. I was kind of surprised. I thought we had one more example for you. Sorry about that. Feel free to rewatch the video as needed. I know it's a little bit lengthy, but you can speed it up if you know how to do that. So we'll come back and look at this again in a future lesson, a little bit cleaner, a little bit faster now that you have this kind of worked out. Have the mapping diagram in your head. That's the important one. All right, we'll talk to you later. Thanks.